Hello, it's Keith here, and this is lesson 14 of the multi-platform series of my Z80 programming tutorials. Today we're going to be looking at some tilemap code. You can see it scrolling away on the screen over here and up here. Now this can also do sprites. It's a tilemap routine, but it can do 8 sprites that are built up of 8 by 8 tiles, and you can see there's intermittently a Chibiko and a Yokobiko flying around the screen, and the sprite can be partially or entirely transparent for that matter. The edges are using 0-byte transparency, which is where all of the bits in a byte are 0. That byte is transparent, but the other ones are not. Now we're going to go over the code and we're going to discuss how this routine works. We're going to be looking at the Amstrad CPC, but to be honest, the code can be easily ported to other systems. It's currently been ported to the Spectrum and the Sam Coupe, and it's almost the exact same code. There's also a Sega Master System version which uses the true tiles and sprites of that system. The code is a little bit different there, but not massively so. So it's going to be the Amstrad CPC code we're looking at today as an example, but most of the stuff here is almost identical on the other systems. So we're just picking one and we're covering that as a way of having something to go through. Now we're going to be looking at the code. We're going to be looking at a much simpler version today. I will show you what we'll be looking at. It's basically going to be split up into sections. The first one is just a basic tile map, and you can see that just here there we go. This is what we're going to be showing today. Now I know it looks quite boring compared to the last one, but it's basically all the same functionality, only it's static now. So we've got a grid of tiles, each of them is 8 by 8, and we are using different graphics for them. Some of them are solid filled. We can solid fill tiles faster. So this is basically a test pattern, and this is what I developed first. When I'm programming for a new system, we get this simple example working first, and then we do the scrolling version, which is where there's a super tile map, which is much bigger. That's calculated into the logical tile map, and then that's used to draw the screen. But the logical tile map and the drawing is being done here just without that extra complexity. So this is a nice easy test to get started on, and it's this that we're going to be looking at today. But as I say, the code that does that is basically almost all the same as the other one. There's just a few extra bits for the extra calculations, but we're going to build this up into stages. So today we're going to be discussing the logical tile map. Now this is the one that's used to calculate what's on the screen. It's stored in a very fast format, which is basically in memory addresses for the data that makes up the bitmap data. We're going to be learning how it's drawn to the screen, how the bitmap tiles are drawn, and also the solid tiles, and finally the transparent tiles, and also the empty tile, which is a tile that is effectively skipped over. This can be used if you've got a very big sprite and 8 by 8 chunks have literally no graphics in them, or if you're using multiple layers of parallax, which this can do, although it is slow. This routine can have multiple, because it's a software tile map, this routine can cope with multiple layers if you so wish. So it's got quite a lot of potential. Now we're going to be going over the code today, so let's go over to today's example and let's see it. So we're going to be looking at this SpeedTile Sprite Simple. This is basically the more limited version, as I say, the one you just saw. This is it running on the Amstrad CPC here. In just a moment when this program loads. There we go. So that's what we're looking at. But it will also compile onto other systems like the Spectrum, the Sam Coupe. Where is it? There we go. So this compiles to the Sam Coupe, and it also compiles to the Sega Master System. And also the Sega Game Gear for that matter, but as I say, basically we can compile this to a lot of different systems, and so this is a very simple test. Now we have quite a lot of definitions. You can see here these are for different platforms, but basically the majority of this is because I had to make some exceptions so that it would work on hardware tile sprite systems where we were addressing literal tile numbers versus software tile systems where we were addressing bitmap definitions of tiles. Now we're going to be looking at bitmap data today because of course we're going to be looking at mainly the Amstrad CPC. Now the tile format is exactly the same format that we used for the YQuest game, so 8 pixels wide, 8 pixels tall in a normal format. That's the general bitmap data, the tiles that are entirely pixel data. We also have filled tiles. These are solid filled. You can maybe see, you can see that some of the tiles are solid filled with a kind of checkerboard pattern, and those are the filled tiles, and they are filled a lot faster because we're basically just reading in 2 bytes and filling the entire 8 by 8 area with them. Now those are stored in a separate area here. The formats are basically quite simple. Now you'll notice we're aligning so that the bottom 2 bits are 0 in both cases. There's a reason for this. Basically, each of our tile definitions use 2 bytes, and these are typically the address of the bitmap data that we want to show in that tile position. Now the tile map is basically rotated through 90 degrees. Now we're basically going down the screen as we go across this data here. That's a more efficient way to draw things. So we're drawing down in this format, but it's actually stored horizontally. So this is 0, 0, this is 0, 1, this is 0, 2. Now t size is the size in bytes, so tile bitmaps plus t size would effectively offset us by 1 tile. Tile bitmaps plus t size times 2 would effectively offset us by 2 tiles. So these are the memory addresses of the bitmap data. Now I know this is confusing, but you don't need to worry, because when we start using the super tile map, the super tile map will kind of help us out a bit. We define super tiles and then we build up our world level out of those super tiles. And what I plan to do if I come to use this for a game is I'll actually write an editor for it, because you don't want to really work like this. It's just an example. We needed some test data. So anyway, as I say, these are memory address offsets to the bitmap data. Basically, scrolling here, basically within the relative section. So the CPC data here is tile bitmaps, and as I say, that's just normal bitmap format in the 8x8 screen format we used for YQuest, and we used for Grime as well for that matter. Now the fill data is in a slightly different format. We have 2 bytes, and they will be alternated for alternating lines of the 8x8 area. We do have to space by 2 bytes to keep the alignment though. The bottom 2 bits have to be 0 for tile bitmaps. That's what defines the normal tile bitmap format. 0, 1 will define a solid fill. We can see that at the top here. So that's the solid fill. The bottom 2 bits being 1 will define a transparent tile, which is where the byte 0 is not drawn. And there's a special case where the top byte is 0 and the bottom bit is 1, and that will be a completely empty tile, which is just totally skipped from the drawing. Again, I know this is a bit weird, but all of this has had to be done for speed of drawing. It's not easy for a human to look at. It's not particularly pleasant to look at for us and easy to understand, but that's because we have to work for what is going to be fastest for the computer to draw, because we're really pushing an 8-bit system to its limits to do this with a software tile map. Now I know some people say, why are you using software tile maps? You should use hardware scrolling, blah blah blah. Well, there's a couple of reasons for that. Firstly, hardware scrolling is more difficult, I think. When you move the hardware, when you hardware scroll a screen, all of the screen coordinates and their relative XY positions in logical space will change, so you'll have to compensate for that. If you hardware scroll a screen, but one of your sprites needs to stay in the same position, you're going to have to redraw parts of the background anyway. Another problem is on my Amstrad CPC, I don't have the original monitor, and my converter box does not like hardware scrolling, so I would be effectively writing a game I probably couldn't play. And the long and short of it is, I think if you're struggling to write a game, if you're new to writing games, and you're probably going to find this quite tough. If you're struggling with this, you're going to struggle even more with hardware scrolling. So I think you probably should just make do with this. To be honest, the vast majority of the classic games from the 8-bit days, the Robocops, the Batmans, all the games everyone remembers as being really good, that they all use software scrolling. Hardware scrolling has become more popular these days because people are getting a lot cleverer, but back in the day it was pretty much all software scrolling anyway, and that's what we're doing here. The example does use 2 screen buffers to keep things smooth with the animation, and we will discuss that as well. Now when it comes to wanting to draw, we're going to use a function called draw tilemap. We specify DE as the address of the tile buffer. Now we're specifying the very start, but we can offset it. Remember, we're going down the screen, and so effectively if we add 2 to this, we will move down 1 tile within the tile buffer, and if we add the height of the tile buffer, which it's configured to 32 tiles, so if we add 64, we will effectively move across the logical tile buffer here. And that's how we do our scrolling when it comes to the super tile map in the later example. But today we're just drawing the entire tile map, and we're not doing any kind of partial scrolling of the tiles either. This is the very simple example we're looking at here. Okay, so let's start having a look at the code that actually does the job. So first of all, we're going to be looking at the SpeedTile normal tile function. This is the basic one that does the bitmap tiles and also the solid fill tiles. Is also the transparent tile function, which is a sort of optional extra. You could disable it if you didn't want transparency. So that's something you can cut out to get started quickly. Now, when we run the draw tilemap function, first of all, what we're doing here is we are working out the starting position of the drawing. Now, we're working in screen bytes here. So we're getting the active bank. The active bank is the top byte of the memory address for the screen base. The screen base is C000 on the Amstrad CPC by default. But if we're using 2 screen buffers, we will need to use that and somewhere else. C000 and 8000 are the ones I'm using in this example. Now, that will cause you problems if you're using disk systems. But we're not. So if you are, then you're going to have to do something else. Either use 4000 or page the disk data out. So that's what Chibi Akamas did. So you got to really work around all of the capabilities of your system and requirements of your software if you're going to do this kind of thing. I'm pushing things very far with this example. This isn't a simple beginner's example. This is something a bit tough. So if you don't understand, I get it, but we've got to start to look at this really kind of complex stuff. I've had requests for this, and I think people don't understand how hard it is. So here it is. Anyway, so we're calculating the bottom byte of the screen address here and the top byte here, and you can see there's some offsets here. Now, this is for if we are basically using a draw that's not the full size of the screen. We do that because we later use this code to simulate sprites. The sprites are drawn with a modified version of this using this draw tiles routine. It's just skipping over this initialization and defining a custom start and size of the graphic to draw. So here we're defining the screen start, and then here we're defining the screen width and height, the height, width and height in the tile map, which is the full screen in this case. Now, what we're doing here is we're defining the number of unused tiles. Now, our physical screen, our visible screen, is 24 tiles tall, but our logical tile map is 32 tiles tall. And if you remember, the memory is going down the screen and then jumping back up. So once we've drawn our 24 tiles, we're still going to have 8 tiles of our 32 tile map that we've not used. So we're going to skip over them. And that's what we're doing here. We're defining that here. This is the number of unused tiles times 2 because there's 2 bytes per tile. And that will be a constant value for drawing the tile map, but as I say, this code is also used for drawing the sprites. So that's why we may need to change it sometimes. Okay, here's our draw tile routine. And you'll notice we're backing up the stack pointer here. And then you will then notice that there's no calls or any pushes or anything in here. We're misusing the stack pointer. I've covered that before. Basically, if you want to read or write data very, very quickly, using the stack pointer to read or write is the fastest way of doing things. So we're misusing that stack pointer, and so the stack pointer here is not a real stack pointer. The stack pointer is actually going to be the graphic data of the tile we want to get onto the screen. Okay, so that's what we're doing there. We're loading C with 8. We're going to need that later. You'll see we're using the shadow registers as well here. So we're going into the shadow registers and loading C with 8. We're then getting our starting draw position here into the accumulator and the number of rows we want to draw in B here. Now, what we're going to do next is we are going to start drawing down the screen. Okay. Now, what we've done here is we've basically transferred the tile map into HL, and then we're loading 2 bytes from the tile map. We're effectively getting a memory address of a tile that we want to show to the screen. This is the bitmap data, or presumably bitmap data. We're swapping it back into HL, and then we're then checking the bottom bit. If the bottom bit is 0, this is a bitmap tile, a normal tile. If it's 1, then it's probably a fill tile, and we're jumping over to custom tile to look at what that's going to be. And that's why the bottom 2 bits are 0 of the tile data, because they're actually being used for other purposes. They're basically being used as markers to define the tile type, which is why we needed to have all of these lines here on our fill data and our tile map data. So that's why we're doing that, and here we're checking, and if the bit is 0, we're doing a normal tile, which is a bitmap tile. We're going to be using 1 byte for each 4 pixels on the CPC, so 2 bytes per line, and we're going to have to move down that individual tile, and then once we've finished the tile, we have to move down to the tile below, because we're going down the screen and jumping back to the top and starting again. Okay, so at this point, HL contains the bitmap data of the tile. We're loading the stack pointer with HL, and then we're popping the bitmap data out of the bitmap. So that's why we're using pop to fast read the data, and we're getting effectively one full line with each pop. So what we're doing here is we're putting DE onto the screen, increasing L. Now I've effectively set the screen to 256 by 192, the Spectrum screen style. This is a lot faster because the normal screen is not byte aligned, but the Spectrum style screen is, and that means we don't need to ink HL after each byte that we write. We can just ink L because we never need H to change to move across the screen, only down, and that's important because it means we're going to be a lot faster. So that's why we're only inking L here. So we write E to the screen, move across the screen, write D, and then we're relying on the fact that the accumulator still contains the top byte of HL. So we're adding C, which contains 8, and that will move us down one line. Now we're popping another pair of bytes out of the bitmap data, but we're drawing them in reverse this time. So we're writing E and D here, but D and E here, and that's because we never decremented L again. So we effectively wrote the byte here, moved down, wrote this byte, and then we write this byte, and we move down, and then we write this byte, and we write this byte. So we're going in a kind of zigzag pattern, and that is going to save us a little bit of time. So each time here we're adding C to the accumulator, which still contains H, and we're updating H, and that's effectively moving us down a line each time. And so we're doing 1, 2, 3, 4, 5, 6, 7, 8 lines in an unwrapped loop. That means no loop, basically. So we're doing all of these as one giant execution with no loops of any kind to save some time. Then, because of the way the screen memory works, we have to do a bit more of a tricky calculation to move to the next line after that. But basically adding C840 will fix things, and that will move us down another line, and it will fix the wraparound of the memory addresses within screen memory. We've been changing the top byte each time here, but now we need to kind of jump back up. So adding this will fix that, and we then just need to make sure the accumulator contains H again, because we've been doing these add C's each time to move down a line. So that's the first tile done of the screen. We've then moved our memory address down a tile, and we're going to draw the next tile. So we repeat until B contains 0. At this point, when we get to here, we've drawn an entire strip of the screen, and we now need to skip those unused tiles within the logical tile map. Remember, there's 8. We need a few to do the scrolling of the later example. So we're skipping those by adding 16 to DE, and DE is the address within the logical tile map of the addresses of the bitmap data, and we're then moving C across the screen 2 bytes to the next column, and we're going to repeat again, just assuming there's more tiles. So we're jumping all the way back up here. As I say, each time HL needs to contain the address of the logical tile map of the bitmap data, and it will do because we've skipped over those unused tiles here. If we didn't do that, then all the lines would end up out of sequence, and it wouldn't be a nice square tile map. It would be all kind of jagged. Wouldn't be very nice. So that's really all there is to it. I mean, because we're working for sheer speed, there's relatively little of it. It's just unfortunately complex. You've kind of got to optimize everything as much as you can. Now, this is the best I can do. I mean, there may be ways of doing it that are better, but I wrote my own code the best way I could figure out how to do it. So if you can do better, good luck to you, but I couldn't, so there we go. Anyway, that's the basic code. If you remember though, we were checking that bottom bit here, and we were jumping to custom tile. Now custom tile here will set the bottom bit to 0, because that was just a marker, and then it's testing bit 1. Now if bit 1 is also a 1, this is a transparent tile. If it's a 0 though, then maybe this is a filled tile, unless the top byte is also 0, in which case it's a completely unused tile. And to move down the screen, basically move down 8 lines, we can just add hexadecimal 40 to HL, the memory address, and that will do that. So that's moving us down a full tile there. So that's what we do if we don't need to draw anything in this square at all. But if we want to do a filled tile, we will end up here. Now at this point the code is almost identical to before. It's basically the same as this, and that's why this is so quick to port. The only difference is we're popping 1 pair of bytes out of DE, and then we're filling each line with D, and then each line with E, and then each line with D, and then each line with E, and just repeating that. It's almost exactly the same, and it jumps right back to here and finishes in the exact same way. The only difference is we've only read in 2 bytes instead of reading in 2 bytes per line. So we save some speed, and speed is very important on an 8-bit system, obviously. So that's the solid fill version and the regular version. And the final version is the transparent tile version. And this is, as I say, this is basically working with a byte 0 is not drawn to the screen. This is how Chibi did its transparency. If you want better transparency, you might want to do an AND followed by an OR. If you want to see how to do that, I've covered that in a previous tutorial, so please check out my YouTube channel and look for that transparency tutorial. But for simplicity and speed, we're doing this one. I think this is adequate for most cases. And what we're doing here is we're just basically almost the same. We're popping DE and we're just checking each byte that's been received and comparing them to 0. We're XORing A, setting A to 0 here. And then if the byte is 0, we're skipping over the write to the screen. If the byte isn't 0, we're just writing it to the screen as normal. Now we're using some set commands here to set H, which is saving us just a little bit of memory, because we're using the accumulator now to compare to 0, where we actually need to increment the accumulator. We're actually having to load A into H and XOR A again. So using a set here has just had the same effect as adding 8 to H without having to mess with the accumulator here. And maybe it's a little bit faster, not much, but maybe a little bit. But basically this is the same again. It's basically the same code as the normal tile code. The only difference is we're comparing each byte to 0 before setting it to the screen. And if you couldn't be bothered to write that and didn't need transparency, for example on the Spectrum, what you could do is basically just check if bit 1 was 0. If it wasn't, set it to 0 and then just run this routine again, and that would work just fine. As I say, it's basically an optional extra in some ways. You can turn it off. But anyway, that's the end of today's example. I know it's tricky. I'm afraid it's going to be. This is a complex thing. If this is too much for you, then I think you honestly need to find a way of writing a game that doesn't need a scrolling tile map. And if you can't think of one, you're probably not being creative enough, because Chibi didn't have one. So there we go. And lots of other games don't as well. So I'm pretty sure you can find a way of not having a real-time scrolling tile map. You just use the flick screen scrolling like games like Dizzy did. There were so many ways of doing it without this. But I know it's something that people want to see, and I was feeling finally confident enough to try and write a viable example to do it, and this is what I came up with. Anyway, as always, you can go to my website, you can download today's example, and you're welcome to use it in your own games and programs and whatever else you can do with it. And if you manage to somehow sell it to make money from it, the best of luck to you, because I'm sure I couldn't. So you deserve all the success you get with that, and you don't need to give me credit if you don't want to. I don't care. Anyway, if you've liked this, please like and subscribe. Liking the videos makes YouTube recommend them to more people, and subscribing convinces me to keep working on them, because I had to take time off work to write this and get it tested for all of the systems, and doing that, you know, is a lot of commitment. So it would just help if people subscribe to the videos and things. Anyway, whatever you do, I wish you all the best in your Z80 programming and hope you have a lot of fun with it. Thanks for watching today, and goodbye.